Hello, and welcome to Agrosive Physics. Today is day 132, and what I'd like to do today is look at the energy level diagrams in our reference table. We have two different energy level diagrams, one for hydrogen and one for mercury. And what you'll see on them is that they both have the ground state on the bottom, and the ground state is a negative value listed in electron volts. Now, if we need to find the number of joules, for example, if we need to figure out the frequency of light that's released or absorbed, we are going to need to convert electron volts to joules. Remember, we have an equation or conversion that allows us to do so. 1 electron volt is 1.6 times 10 to the negative 19 joules. So that will allow us to go back and forth between joules and electron volts. Now, on the reference table, you'll see that the ground state is on the bottom, and for hydrogen, you list up the energy levels by number. For mercury, it lists it by letter. Now, when we want to analyze the energy level diagrams, what we need to do is subtract the energy levels from one another. For example, if we want to know the energy released when an electron jumps from the third energy level in the hydrogen atom to the first, what we're going to need to do is take the value of the energy level of the third and then subtract it from the energy level of the first. So in that case, we would just do subtraction. In fact, our reference table lists an equation for energy of a photon as E1 minus E2. Hopefully you don't need to look in the reference table for that, but you're going to find the difference between the energy levels involved. Now, when an electron's in the n equal 3 energy state, it may not just jump straight to the ground state. It could possibly jump to the n equal 2, then the n equal 1. So you can have three different forms of light that are released when an electron jumps from 3 to 1 in the hydrogen atom. You could have 3 to 2, so subtract those two numbers, 2 to 1, subtract those two numbers, or 3 to 1, subtract those two numbers. Each one of those are listed in electron volts, so you'll need to convert to joules and then possibly do E equals HF if you want to know the frequency, or E equals HC over lambda using the H as Planck's constant, 6.63 times 10 to the negative 34 joule seconds. Either way, we can go from looking at the chart to finding a numerical value using subtraction, conversion, and then the equation that we have for the photons of light. The values are negative for the ground state because when you take an atom or an electron in an atom and you bring it closer to the outer shell, you are bringing it, the way I look at it, closer to the ground level, outside the atom. Once you reach the shell, the outer shell, you're at zero energy. And then when you are removed, anything left over is given to the electron. So if you're going inside the atom itself, you need to jump exact amounts. So in order to jump from n equal 1 to n equal 2, you have to subtract the two different values of the energy levels. Anything else won't work. The only time that you can have an excess amount of energy is to ionize. So if you are in the ground state of hydrogen, 13.6, and you hit the electron with a photon of 15 electron volts, you would do 15 minus 13.6, and you'd end up getting 1.4 electron volts of kinetic energy left over. Now, the kinetic energy is into that electron as it moves out of the atom. Well, if you know kinetic energy, and you can convert it to joules using 1 electron volt equals 1.6 times 10 to the negative 19 joules, you could then figure out how fast it's moving using kinetic energy equals 1/2 mv squared. A classic problem on the state assessments is figuring out how fast electrons move once they're ionized. So at this point, we can realize that the energy level diagrams don't have even steps. They start negative and end at 0. You need exact amounts of energy inside the atom, but you can have any amount of excess outside once you're ionized, and the excess goes to the electron itself, which then turns into kinetic energy. I think at this point what I'd like to do is a couple of sample problems and show you exactly how we would use the reference table to do a few sample problems. So let's take out the whiteboard now and do that. Thank you. Now, a byproduct of the Bohr model of the atom is that we have energy level diagrams. And the electrons within the atom will jump up or down to specific levels. And what's important about the Bohr model is it has to be an exact amount. So kind of like a set of stairs, in order for electrons to get to a higher stair, it needs to have a specific amount. It can't be in the middle of the air. So the electron can jump, but in order to jump there, it can't have excess or too little. Obviously, too little makes sense because you couldn't get up the stair if you didn't have enough energy. But it's not going to do that kind of jump where it goes higher than lands on the next level. It has to have an exact amount. And basically, the point of energy levels is that the electrons are stable at that point. Of course, they don't want to stay at that. They're not stable for long, but they exist in basically standing wave patterns at the different energy levels. So electrons, when they jump up to higher energy levels, if we move up, we gain energy. And if we move down, it releases energy. Now, when it releases energy, what will happen is we'll have photons of light being released. So that energy is going to be released as light. And what we can do is actually find the frequency, or if we wanted to, the wavelength of the light based on the energy. Now, the energy level diagrams that we deal with on the state assessments list the energy levels in electron volts. So when you're using the reference table, the values are in EVs. Now, in order to convert, this has to be in joules. So 1.6 times 10 to the negative 19 joules is 1 electron volt. So we just have to remember that conversion. And if you forget the conversion, it's of course on the front page of the reference table. Now, when we're looking at the chart in the reference table, and it's right in the center of the reference table. If I were to take out the reference table now, what I'll do is I'll show you an example of the energy level diagrams that we have. Here are the two that we have for our assessment. We have hydrogen and we have mercury. And you'll notice that each one has a set of lines where the electrons will jump from higher to lower energy levels or lower to higher. And what we're going to do now is look at an example or two of specific jumps and calculate the energy involved. Now we have a sample problem here where the electron is in mercury and it's going to jump from level I to E. Now for the hydrogen atom, we list the energy levels as n equal 1, n equal 2, n equal 3, etc. So this is for hydrogen. For mercury, what we have is A, B, C, D, etc. So we have letters instead of numbers. And if we're in the I level, according to the reference table, the value is listed as negative 1.56 electron volts. Now the reason they're negative is because they have at the surface of the atom, that's considered zero energy in terms of the electron being removed. That top line is also known as the ionization line. It lists ionization on the chart. And in this case for mercury, the J line is ionization. If we give an electron more than is needed to remove it from the atom, the electron will take that energy and then be removed. And what you'll do is subtract the amount of energy. For example, if we're in the I energy level and I give it 2 electron volts of energy, what will happen is the electron will be removed. It'll be kicked out of the atom. It'll be ionized. And what we would do is take 2, which is what I gave it, and subtract from it 1.56, which is what was needed. So 2 minus 1.56, and that's going to be 0.44 electron volts of energy. That would be the kinetic energy given to the electron. And what we can do from that is determine perhaps how fast the electron moves as it's removed from the atom. Unfortunately, within an atom, you have to have an exact amount of energy. It doesn't work in this manner within the atom. This only works if you actually ionize the electron. So you have to remove it from the atom. But in our example, we have an electron in the I level, which is negative 1.56, and it's going to jump down to the E level, which according to the chart is negative 3.71 electron volts. Now I know they're both negative signs, and subtracting negatives can be confusing. But what I like to do is just use the absolute value, and I just find the difference between the two. So I'm going to do 3.71 minus 1.56. And I know that if I'm moving down in terms of energy levels, I'm going to be releasing energy. So the energy that's being released is 2.15 electron volts. That's the difference between these two. Now that energy needs to be converted to joules. And I'm going to use my conversion factor, 2.15 eV. 1 eV is 1.6 e negative 19 joules. So times 1.6 e negative 19. And I have 3.44 times 10 to the negative 19 joules of energy. Well, if I want to find the frequency of light that's released, I'm just going to do E equals HF. So 3.44 times 10 to the negative 19 joules equals 6.636 times 10 to the negative 34 joule seconds times frequency. And when I calculate the frequency, divide it by, and for our reference table, the value for H is 6.63. So I'll use our actual value on the reference table because they're going to use that to do multiple choice questions, and I want to make sure I have the right precision. So my answer is going to be 5.2 times 10 to the 14 hertz. Now, a secondary question may be, what type of light does that represent? Now, if I look on the chart, what I see is that 10 to the 14 hertz goes from the infrared to the visible all the way to the ultraviolet. So there's a big range between it. However, if I look at 5.2, that's within the visible spectrum. And 5.2 times 10 to the 14 is exactly in the middle between green and yellow. So it is actually one of the numbers that differentiates between the two bands of colors. So I would say that it's a green-yellow light, definitely within the visible spectrum. So even with the simple question of what happens when an electron jumps from higher to lower energy level, we may have to convert, we're going to have to subtract, we're going to have to calculate E equals HF or E equals HC over lambda, and then we might possibly have to look on our reference table to figure out what type of light we're dealing with. So a simple question with energy levels can turn into 4, 5, or possibly even 6 steps to get our final answer. A lot of work for a single multiple choice, but easy points if you know what to do.